Hello and welcome back to my channel, and today we're going to be proving that a hanging chain forms a Cosh curve. So first we're going to draw a large diagram and we're going to take our time over it, because if we take our time over the diagram then we likely will start the correct way. So I've drawn my y and my x-axis, and then we're going to have a support here and a support here, so B and B prime. They're just supports for our chain, and our chain is going to hang between them like this. It probably wouldn't hang exactly like this, but we're going to say I'm going to make it hang a bit deeper, like that. And we're going to have a point A at the bottom. So A is the bottom of our curve, curve our chain. And we're going to have P as another point. The distance from A to P along the chain is S. So first of all, we're going to draw on the forces that there are going to be. So I'm going to draw these in red. There's going to be a tangential force at the bottom. I'm going to call it T0. There's going to be the weight of the A to P. And then at P, we're going to have another... set up my diagram again. Ugh. So frustrating when this happens. And at P, we're then going to get another tangential force, which we can form a triangle with angle theta, and we're going to call it T. We're going to have T cos theta and T sine theta as horizontal and vertical components. Okay. So now we're going to resolve vertically. So resolving vertically, we get W is equal to mg. But what I'm going to introduce is a variable called lambda, and lambda is equal to the mass divided by the length. The length in this case is S, so lambda S is equal to the mass. Therefore, the weight is equal to lambda SG. Okay, and we know that the only other vertical force is T sine theta. So T sine theta is equal to lambda SG. That is our first equation, and we're going to call it equation 1. I'm going to... Shall I do it? Yeah, I'll do it in blue. I'll do it in blue. Equation 1. Just so it's easy to find later, because I will be referring back to all of these equations after we've formed them. The next equation we can form is by resolving horizontally. We get that T0, the tangential force, I should say, is equal to T cos theta, which is the horizontal component of T. Now we can find the gradient of the curve as well while we're at it. So we can find that dy by dx is equal to T sine theta divided by T cos theta. The t's will cancel and we get sine theta over cos theta. So therefore dy by dx is equal to tan theta. And also, given that I know what sine theta and t sine theta and t cos theta are, I can rewrite this and say that dy by dx is also equal to lambda SG divided by T0. Okay. next, I'm going to... I think there are too many variables. I mean, we've only got 4, but I'd like writing fewer letters. So, I'm going to say let A equal T naught divided by lambda G, because that takes out a number of our variables. And first of all, we need to determine the units of A. So, by dimensional analysis, A is equal to T naught is a force, so has F equals ma, so it's going to have a mass. A has units, so length t to the minus 2, divided by lambda is mass per unit length, times g, which is another acceleration, t to the minus 2. So we can cancel this with this, and this with this, and we just get 1 over L to the minus 1, which is just L. So A has units meters because it is a length. Now we're going to convert equation 3 to equation 4. I haven't labelled it, have I? Naughty me, naughty me. So equation 3 is tan theta is lambda sg. This is equation 3, but really all this is equation 3, which is not very helpful, but bear with me. Thank you for your patience in advance. So equation 3 goes to equation 4 by substituting a in. So we're going to say that tan theta, or dy by dx, whichever you prefer, is equal to s over a, which is a lot simpler. So we're going to say that dy by dx is equal to s over a. Now, what we're going to do, because what we need to do is find an equation for the line y equals. And at the moment we've got dy by dx. And if we were to just integrate this, we wouldn't get a very satisfying answer. Or we wouldn't get us an answer that tells us anything. So what we're going to do is we're going to differentiate again, or we're going to do some rearranging, and then we're going to differentiate again, and then use our results to integrate twice to get y. That will make more sense when we do it. So, first, note that ds, which is the small length ds, you could put this in brackets, but you don't need to, because it's ds is just a length. That is equal to the square root of dx squared plus dy squared. Dx and dy are both just lengths. So, for example, if you were to draw a right angle triangle, dy is the rise, dx is the run, ds is the length of the hypotenuse. Okay? So, we're now going to divide both sides by dx. So ds by dx, if you were to differentiate s by dx, you get square root of dx squared, that's the 2, plus dy squared over dx. If I'm to take the dx into the square root, I'm going to need to square it. So ds by dx is equal to the square root of 1 plus dy by dx all squared. I'm going to write that more neatly. Plus dy by dx all squared. When I get excited, my writing deteriorates, which is not the best thing. Anyway, we've got this equation, and we're gonna do some more work with this. So we've created this. So this is our note. We're now going to differentiate again, like I was saying. So d by dx of dy by dx is d2y by dx squared, but that is also equal to d by dx s over a. Now I want to get rid of the s. So what I'm going to do is I'm going to differentiate it with respect to s, but I'm also going to do something else to mean that it sort of cancels out, which you'll see what I mean. So d2y by dx squared is equal to ds by dx s over a what am I going to do? ds d by we'll get there. D by ds. So differentiate this with respect to s, which is just going to get this s to go to 1. This s to go to 1 specifically. And then multiply that by ds by dx. Because then you could say that these ds's will cancel, but that's not really how it works. But nevertheless, if it helps you understand, that's great. So now we can do this. So we get that d2y by dx squared, and this is going to be equation 7. So I'm going to get out my blue marker. Equation 7? I've only created 6 equations. I've only even created 5. Yeah, I'm going to create equation 5. I don't know where 7 came from. Anyway, maybe I just like 7. A bit of an odd thing to like, but anyway. Nevertheless, it's a biblical number. So d2y by dx squared is equal to 1 over a times ds by dx. But we know what ds by dx is because we found it in our note. So d2y by dx squared is equal to 1 over a times the square root of 1 plus dy by dx squared. Now, once again, I think I've got too many variables, so I'm going to let p equal dy by dx. Just rewrite that. dx. There we go. So therefore, dp by dx is equal dy to d2y by dx squared, which is equal to 1 over a times the square root of 1 plus p squared. Now, in order to integrate to get something in terms of like x equals, so we need to rearrange for just dx. So we're going to multiply both sides by this and divide both sides by this. So we get that dp, or the adp over the square root of 1 plus p squared is equal to dx. Now, if you watch my last video, your brain, your mathematical antenna will be tingling, because in the last video we found that this is going to be note mark 2. Should we call it note mark 2? Note mark 2. That the derivative of r sinh x, or p in this case, is equal to 1 over the square root of p squared plus 1, which is almost what we have here. So if we integrate both sides, because at the moment we're dealing with dp by dx, so we really want to get to p, which is dy by dx. So, because then we're heading in the right direction. We can take out a, because a is a constant. dp over the square root of 1 plus p squared. That's the same as writing a times the integral of 1 over 1 plus p squared square rooted dp. That's the same thing, but you can write the dp like this, if you wanted to. And that will be equal to the integral of dx, which is really the integral of 1 dx. So therefore x, I'll write it on that side, sorry. X will be equal to a r sinh p by our note here, plus c, the constant of integration. Now we're just going to evaluate for c. So at x equals 0, this will equal 0. R sinh p is a times the is natural log p plus square root p squared plus 1. So at x equals 0, tan theta will be equal to 0, and the gradient will be equal to 0, so p will be equal to 0. So what we have here is root 1, which is just 1. So a times the natural log of 1, which is 0, a times 0 plus c is equal to 0. Therefore, c is equal to 0. So we have that x is equal to a r sinh p. Now we're going to rearrange to get dy by dx, which is rp. So divide both sides by a. X over a is equal to r sinh, I'm going to write it as dy by dx now. And then dy by dx is equal to sinh x over a. Now all we need to do to get our function of y is, or our function of x in terms of y, is just to integrate both sides. So if we integrate the left side, we just get y. Integrate the right side, we get a cosh x over a, which is what we wanted. We wanted a hanging chain of uniform mass distribution to be represented as a Cosh curve. So just to show that sinh x over a differentiates to this, sinh integrates, not differentiates, it integrates to Cosh, and you need to, by the chain rule, you need to divide by 1 over a. And if you divide by 1 over a, then you get just a times cosh x over a. Anyway, so that's the proof that a hanging chain is forms a Cosh curve, or a catenary. Thank you for attending this video, and I look forward to seeing you all next time.